Hey everyone, welcome back to Probability Theory. This will be lecture 7 of the course. And in this section, we're going to discuss the multiplicative and additive laws of probability. These are going to be two laws that are very helpful when we're trying to identify the unions and intersections of events. So let's go ahead and jump into it. So we'll call this section 1.7. The multiplicative and additive laws of probability. And so we'll just start with the theorem for the multiplicative law, and then we'll talk it through. So let's start by just stating the theorem. This is what we're going to call the multiplicative law of probability. Okay. And so it just says, given two events, A and B, probability of the intersection of A and B, probability of A and B, is equal to the probability of A times the probability of B given A, which is going to be the same as the probability of B times the probability of A given B, right? So this is the conditional probabilities here. And further, if A and B are independent events, then the probability of A and B is equal to just the product of the probabilities of A and the probability of B. Okay, so the probability of the intersection is equal to the product of the separate probabilities in the case of A and B being independent. And if A and B are not independent, right, and remember the last section was about independence, then we have to, in calculating the probability of the intersection, we have to take into account the conditional probability, right? And so you may be looking at this and saying, oh, I can see what's going on here. This is the probability. In the previous section, we said the probability of B given A was equal to the probability of A and B divided by the probability of A, right? So we said that in the previous section. And so here you see this is really just a rearrangement of the definition of conditional probability. Right, and then so down here, of course, this is that if the two are independent, then the conditional probability, then the intersection probability looks like this, right? I.e., the conditional probability isn't existent. Okay, now we could prove this because I just kind of talked you through that. But what does the proof look like for something like this? Well, let's let A and B be two events. Then, of course, what I just said was the probability of A given B equals the probability of A and B divided by the probability of B. And that means that the probability of A and B equals the product of the two, equals the probability of B times the probability of A given B. Okay, and then this is just one of the three cases, right? So we showed this one, this one. This one is almost exactly the same, and then this one, when you assume independence, then here is just equal to the probability of A, isn't it? Right. Remember the conditional probability of A given B. If A and B are independent, is equal to the probability of A, and so you can see where that comes from. Okay, so I'll just write out the one, but yeah, so you can see how this works. It's really just a immediate consequence of the definition of conditional probability. Now, this theorem can be extended to events beyond just two events. So this can be extended to more than two events. I'll give you an example of what that looks like. So if I had the probability of the intersection of A, B, and C, something like this, then I can think of it in this term. I can think of it as the probability of A and B as an event and C, right? And so if I do that, then I can just apply what's up above here, right? And I can say that this is equal to the probability of A and B times the probability of C given A and B, right? So that's just using the theorem, right? I'm thinking of this as event 1 and event 2, right? So I can kind of break it up like this. And then I can further break this one up. Right? So this, instead of the probability of A and B, this is the probability of A times the probability of B given A, and then times this last thing, probability of C given A and B. Right, so this part here, is just from this. And this part here comes from this idea, right? Well, actually the whole thing, but right. So you can kind of daisy chain these together, and then of course, if you had a fourth, a fourth event in the intersection, you could just follow this pattern and extend it indefinitely. Okay, so that's nice to know that you just have to kind of think through. You just have to think through this pattern, but it's relatively straightforward if you just take the events and think of them as at two at a time and just kind of keep breaking them apart. So that's the multiplicative law of probability. Okay, now before we get into examples, let's talk about the additive law of probability. Okay, so the next theorem. So this is the additive law of probability. Okay, and so what does that say? Well, it says given two events, A and B, the probability of the union A or B, probability of A or B, is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, and then of course, if the intersection is empty, so if A and B are disjoint, or the intersection is empty, however you want to think of it, then the probability of A or B is just the sum of the two. Okay, and this will look real familiar to people, in regular set theory. You talk about the union A or B, and this being the intersection A and B, right? If you were to add everything from A and add everything from B, you would have added the intersection twice, and hence the subtraction, right? So everything in A plus everything in B, you counted the intersection twice, and so that's why you subtract it off. And you don't have to subtract it off here, of course, because in the case of A and B being disjoint, the intersection is empty, right? So in that case, you count everything in A and everything in B, and there's no double counting anywhere, right? So you'll recognize this from set theory. And so that's really kind of the idea behind the proof. All right. Very good. And then just one more thing that we want to state here. And this is a simple thing, but it's extremely useful. And that is this little theorem. If A is an event, then the probability of A is equal to 1 minus the probability of A complement. And hopefully that makes sense, right? So if I have some space, sample space, and I have an event in there called A, if I want to know the probability of A, this thing, one way I can do it is take the probability of the sample space, which is 1, and subtract off everything that isn't A. Right? And of course, what's left over is A. Right? And so this is relatively straightforward. Okay. But extremely useful. Lots of times, explicitly calculating A might be difficult, but calculating the complement of A is not difficult, right? So this is when that can come into play and be very, very handy. Okay, excellent. Let's do some examples to make sure we can see the usefulness of these theorems. All right, so let's do an example. This is a smoke detector example. So a smoke detector systems has a device A and a device B. A smoke detector system has a device A and a device B. Okay. If smoke is present, the probability that it will be detected by device A is 95%. So if smoke is present, the probability that it will be detected by device A is 0.95, right? And then by device B, the probability is 0.90. So 0.90. And the probability that it'll be detected by both is 0.88. Okay. All right, so there's a setup. You got two devices, A and B. If the house is on fire, if there is smoke, the probability that it will be detected by A is 95%, and the probability that the smoke will be detected by B is 90%. So the probability that it'll be detected by both turns out to be 0.88%. Now the question is, two questions. The first one is, find the probability that smoke will be detected by either A or B. So basically, find the probability of A or B, right? That it'll be detected by A or B or both. And then the second is find the probability that smoke will be undetected. So what are we talking about there? So just to put this in, this is detected by A or B. And secondarily, we want to know the probability that smoke will be undetected. So that would be not A and not B. This is undetected. Okay, so that's what the questions are. So what are those probabilities? Well, this is really pretty straightforward application of the previous three theorems. And so let's start with number one. Right, so for the first one, the probability of A or B, that's equal to the probability of A. This is the additive law, A or B, the union. It's equal to the probability of A plus the probability of B minus the probability of A and B. Okay. Right. And so obviously we know that the two are not mutually exclusive because we're told here that the probability of both is 0.88. So meaning, and just intuitively the example would indicate that they would not be. They would have an intersection. And so you can just pull those numbers off and plug them in. So this would be equal to 0.95 plus 0.90 minus 0.88. And you can calculate all of that, and I think you'll get 0.97. So there's a 97% chance that one of the two, at least, will pick up the smoke, will alarm you when smoke is present. Now, what about the second? What's the probability that it'll be undetected? Okay, and so you can kind of see that that's probably going to be the complement of this, isn't it? But let's go ahead and let's run through the exercise. So the probability of not A and not B. Well, you can think back to your set theory. This is going to be equal to the probability of the complement of A or B, which is what we just said. Okay, and so that's, of course, going to be equal to, theorem 3, which would say that this is equal to 1 minus the probability of A or B. Okay, now we just calculated the probability of A or B right here, didn't we? Yep, so this is going to be equal to 1 minus 0.97, and so this will be equal to 0.03. So a 3% chance that the smoke will be undetected. All right. Very good. Let's see some more examples. What about, we'll pull out some dice examples. We roll a fair die. And we define events. So two events, we'll say event A is the event that the outcome is even, and event B is that the outcome is greater than 3. Okay, so what is the probability of A or B? Okay, well, again, we could think this through and say this is equal to, actually, let's do the intersection first. Probability of A and B. Let's do that one. Well, this one is straightforward, right? You just got to kind of think about what the events are. A is outcome is even, so i.e. it's 2, 4, or 6, right? So, and B is the outcome is greater than 3, so that's going to be 4, 5, or 6. So the probability of A and B, what's the intersection of these two events? Well, it's going to be 4 and 6, right? So that would be 2. There's 2 possible outcomes here. And out of how many total? 6, right? 6 possible outcomes. And so the probability of the intersection will be 1/3. And so then, secondarily, let's calculate the probability of the union. So either even or greater than 3. So that's going to be equal to the probability of A plus the probability of B minus the intersection. So the probability of even is 3 out of 6, so 1/2. 1 second, make sure it's focused here. So 3 out of 6, or 1/2. So we will say 1/2. And the probability of B is, again, another 3 out of 6, so another 1/2, minus the third for the intersection that we just calculated. And so this would be basically 1 minus 1/3, which would be equal to 2/3. Okay, so just a straightforward use of the law, the additive law, right? And then this one we just kind of had to reason about. All right. How about another example? Let's let A and B be independent events. A and B are independent events with the probability of A equal to 0.5, the probability of B equal to 0.2. Let's try to find some different things. So the first thing I want to look for is a probability of the union, A or B. The second thing I want to look for is the probability of the intersection of the complement, so A complement and B complement. Okay, and then the third part here that we're interested in is the union of the complement, so the probability of A complement or B complement. So here we got to be a little bit, we got to think a little more. These might be a little trickier, right? You've got intersections and unions of complements and things. So let's kind of see where this takes us. We'll just start with 1. This one seems straightforward. The probability of A or B. Well, we're given the probability of A and of B separately, and we know that they're independent, meaning they have no intersection. So what is this? This is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, and so that means this is the probability of A plus the probability of B. And then instead of the intersection, because they're independent, this is equal to the product of the probabilities because of the multiplicative law, right? So this would be minus the probability of A times the probability of B. Right, so you've got the additive law that kind of gets you this part. And then this thing here, how do we deal with that? Well, we use the multiplicative law on that section, right? So because A and B are independent, the probability of their intersection is equal to the product of the separate probabilities. And then we have all these values, so we can just plug them in. So the probability of A is 0.5, probability of B is 0.2, and then the probability of A times B is, of course, the product, 0.5 times 0.2. And when you do all that math, you will get 0.6. When you multiply everything together there. So that's part 1. What about part 2? Part 2, here we're looking for the probability of A complement and B complement. Well, how do we do this? How does this work? Well, the key here is to recognize that if A and B are independent, then A complement and B complement are as well. So that's kind of the key to breaking these apart, right? We're told that A and B are independent, and the implication is that the complements must be independent as well. And so that being the case, this is straightforward. This probability of A complement and B complement is just equal to the probability of A complement times probability of B complement. Okay, and of course we know that we know from earlier that probability of A is equal to 1 minus probability of A complement. Okay, and so that's going to play into how we calculate these guys, right? So probability of A complement must be 1 minus a half, and so it's 1/2. And the probability of B complement is going to be 1 minus 0.2, and so it's going to be equal to 0.8. All right, and so when we multiply those together, we get 0.4. So that's not too bad. Again, the key here is just to recognize that the independence of A and B means their complements are independent as well. And then what about 3? So for 3, what are we trying to do here? We've got the probability of A complement or B complement. Okay, so let's kind of write this out and see let's use the additive law here. So this is the probability of A complement plus the probability of B complement minus the probability of A complement and B complement. Okay, this would be, so this we know, and this we know because we just did it, right? So we have all 3 pieces, and so this would be equal to 0.5 plus 0.8, again, just using the same reasoning as above. And then this third piece we found to be 0.4. All right, straightforward. So that means this must be 0.9. Okay, very good. Very good. Let's do one more example. And this one we're going to kind of justify. This will be more like a proof kind of demonstration example. So let's assume A and B are independent. So we have independent events, and let's show that A and B complement are also independent. Assume A and B are independent, and we'll show that A and the complement of B are also independent. Right? So this is to the previous example, we said if A and B are independent, then their complements are too. This will be like one case of kind of getting to that truth. So let's talk through how we might demonstrate this. So the key, there are different ways to show this, but a nice way to show it is to notice the following. A, the event A, is equal to the union of A and B and A and not B, right? So A is equal to A and B or A and not B. Hopefully that's clear, right? A is going to be the element of A is going to be equal to the union of everywhere it overlaps with B and everywhere it doesn't overlap with B. So we're just kind of adding B into the mix by doing this. So note this, and also note that this guy here and this guy here are disjoint. So A is equal to this, and A and B is, sorry, A and B and A and not B are disjoint. All right, so meaning the intersection between these two sets is empty. Okay, and so what we can do is we can use the additive law. So the probability of A equals the probability of A and B plus the probability of A and not B. Okay. And of course, if we can do this, we can just kind of rearrange this. All right, so we'll just do a little algebra, rearrange, and specifically get this thing by itself on one side. So we'd say the probability of A and not B is equal to the probability of A minus this, minus the probability of A and B. Okay, and let's just kind of hold this in memory for a second. All right, so now what we know, we're told, right, an assumption in the proof is that A and B are independent. All right, we assumed that A and B are independent. We assume that they're independent, so that means the intersection is equal to the probability of A times the probability of B, right? So this is kind of an aside, right? When we assume A and B are independent, we get this, right? And so that being the case, let's go back to this thing here that we left off, and let's rewrite it. So that means this is equal to the probability of A minus, now instead of the probability of A and B, let's write probability of A times probability of B. Okay, and so that's the probability of A times the probability of B. Okay, and so what have we got so far? So the probability of A and not B is equal to the probability of A minus the probability of A times the probability of B. Okay, and you can kind of look at this and say, oh, I think we're probably going to factor out a probability of A, aren't we? Indeed, we are. So we do that, and we're left with 1 minus the probability of B. So just some algebra there. Okay, and then we know 1 minus the probability of B, that is equal to probability of not B. All right, and there we have it, right? So let's summarize. So the probability of A and not B is equal to the probability of A times the probability, sorry about that, probability of A and not B is equal to the probability of A times the probability of not B, right? And that's the definition of independence. So A and not B are independent. Okay, so that is a way to show that. And you could use this as sort of the inspiration, and you could, extend this to, well, if A and B are independent, then not A and not B must be independent. That would be kind of the next thing to try to do, right? And you could use this same kind of flow as the blueprint for how to write that proof. Okay, very good. So that's where I think I'll end this section. And in the next section, we'll get into calculating the probability of events using a different method, one that's called event composition. So slightly different than what we talked about a few sections back when we talked about using the sample point method. So until then, take care, everyone.